is Darrell Webb, and I'm here along with the team 172. Also my teammates here, as we have them right here, Kendal and Sergio, and we're here to present our senior design project for the steadiness tremor measurement system for telemedicine. Let's get a background on what tremors are and how they affect. A tremor is an unintentional oscillatory rhythmic body segment motion that can be caused. That for our particular project, we're taking a look at hand tremors. Now, there are different types of tremors. There are resting tremors and there are action tremors, and we're going to be looking at the action tremors mostly, and they can be caused by several things. One, they can be caused by Parkinson's disease, which we are going to explore, and we all have a natural tremor that occurs in each and every person here. Okay, now let's take a back. Let me give you a background on telemedicine. Telemedicine is a two-way patient-clinician communication that will allow the patient to be monitored from another location without actually being physically present with the doctor or the clinician themselves. It includes automatic remote monitoring and testing, and also one of the reasons we want to explore this because it's going to improve the health of the patient by using current technologies that we have right now to remotely monitor what's going on with the patient. So therefore, the purpose and goal of our project is to design, build, and test procedures and systems to quantify the severity of upper extremity tremor or steadiness. One of the design requirements that was given to the team from Dr. Kondrasky, from our sponsor Dr. Kondrasky, was to take a subject, and to the subject under the test using a motion measurement device that we'll discuss later. The information from these tremor will be sent to a local PC, and from there it will be able to be accessed from a central server through a web page. Okay,
a few design requirements we had for our system was for the measurement device to at least be able to measure 2 degrees of freedom, vertical motion and horizontal motion. Some key data aspects we had to take into consideration that we want to be able to measure at least 0.1 millimeters of movement to 100 millimeters of movement. Another thing that we had, that we found out that tremors as an entirety have a frequency range between 3 and 15 hertz, so our device would have to at least be able to measure twice that for our information to be valid. We want to be able to also to obtain raw amplitude movement and be able to plot that by time, and with that information we want to be able to represent it with a single number overall steadiness representation of measurement. Some constraints that we had for this project was to follow the basic telemedicine and remote measurement framework that Darrell mentioned in previous slides. We also had to be able to have the information pass through USB interface because we wouldn't be connected to a PC, and for the device to be powered by the USB. One important other constraint that we had was for the test procedure to be simplistic, so that anybody will be able to go through the entire test without needing too much help from any outside source. One big design option that we had to account for was what measurement device are we going to use to measure these tremors. So normally tremors are usually measured using accelerometers, gyroscopes, or a combination of both. But we want to take the approach of using a vision-based sensor, mainly the Pixicam, which we'll get into later on what that is and what that is for. Some important things about vision-based systems is that it's non-contacting, the existing, pretty much everything, the existing cameras, laptops, cell phones. So if we're able to implement this vision-based system and the measuring tremors, you know, the scope of where it can be used is enormous.
Okay, let's talk a little bit about what we're using for the data acquisition. We're using the Pixie Cam, which was developed by Carnegie Mellon Robotics Institute, and it's not only just a camera. It is a vision-based system. It's a vision tracking. It's a motion tracking and vision system that is perfect for our particular purposes. Since we're going to be tracking more than one item, we're going to be tracking these three colors. We're able to track those items and use the serial data output from the camera itself to communicate with the PC. We also like it because it's an open source product and it's quite affordable. It's only about $75 for the camera itself. Okay. And how the Pixie Cam works. In our senior design project, we're going to take the Pixie camera itself, along with a hand that's going to be placed in front of it from the front view of the camera, and it's going to track the data from some LEDs that we're going to have attached to the hand. It's going to track them and put out the data in this format that we'll be able to use for data collection and data analysis. The LED glove design, we're going to use a glove that's going to incorporate 3 different color LEDs, red, green, and blue, and we're going to track those 3 objects, those 3 LEDs with the Pixie Cam. Now we chose to use LEDs rather than colored balls because they help to solve a problem that was really one of the key problems we had when we were developing the software for this project.
This is our system block diagram divided into 3 sections: motion measurement device, local web PC application, and central server where all the data is collected. In the motion measurement device, we have the microcontroller UNO that's connected to the Pixie Cam. It communicates to a SPI protocol. We have a motor driver that's connected to the microcontroller UNO as well, where it feeds information to the stepper motor for the linear motion movement. We have the PC application where the patient will access and will start the test and communicate to the central server for data collection. This is the pin layout of our hardware system. You can see here the motherboard as an Arduino Uno with the daughter board, which is the driver in this case, connected to, it plugs into the Arduino Uno. Pixie Cam is also connected to the Arduino Uno. The stepper motor is connected to the driver, motor driver for linear motion. The Arduino Uno sends all the data via USB cable to a local PC. These are some of the specifications, voltage specification and currents for each device that we're using. Our system overview of our project. Here on number 1, obviously we need a patient hand with a color-coded block, which in this case are LEDs. 2 and 3 are the Pixie Cam and data transferring unit. We have a number 4 as linear displacement with a lead screw in the stepper motor. Local computer where the patient will access directly, and a remote server where all the information will be stored.
Okay, I'm going to give a quick overview of our auto-ranging system. The reason we chose an auto-ranging system because if the patient is going to be doing the test, and if the range of motion is so the tremors are so bad that being close to the camera would actually reduce the resolution. We decided that we were going to develop an automated system so that it will allow the camera to be moved back, and which will cause it to be further away from the patient's hand, which will decrease the apparent size of the oscillations, so that it's able to we're able to gather data better. And as you can see, we are using the Pixie Cam and the stepper motor with a predetermined number of steps to move it back and forth, so that we're able to remain within the range of delta Y, as you can see from the flow chart for this particular program.
Here is some the calculations and the results from determining how much movement the linear displacement system needed to make. So at the bottom of this graph, it has the object distance away from the pixie, that corresponding resolution with taking into account 320 pixels, and that resulting height in the window, what we call a window that the pixie sees. So going back to our previous constraints in the beginning of the project, we want to be able to measure at least 0.1 millimeters of amplitude, and the maximum is 100 millimeters of amplitude. We want to be able to have a range of measuring both of those. If we decide to move have a displacement system move at least 10 centimeters, well, the resulting resolution we can get is a minimum of 0.5 millimeters of resolution to 1 millimeters of resolution. After consulting with our sponsor, we found out that this will be okay for this system, for our proof of concept and everything. But we do expect a future higher resolution camera of the Pixie to be developed, which will result in an increasing resolution in both axes.
In this slide, we have the tentative web page structure. This is tentative because this is how we envision to be the next phase of this project. We have a 4-level web page with a level 1 home page and a couple options for either a patient or a healthcare provider. Level 2 is a sign-in option, with it's either a new patient or existing patient. If it's new patient, we'll go to a level 3 where all the data will be stored with some credentials of the patient. Level 4 will have the options of 2 different tests in the time of the test, which is 15 seconds. Tentative operation scenario. Right now, we access a web page through this URL. This URL is alive. It's been done with Node-RED with a couple buttons and a chart for the purpose of testing this project. It will go through a test start button. It will go into calibration arrow ranging for a few seconds, start collecting data for 15 seconds, and repeat or finish as needed per the patient's discretion. The clinical scenario will be for the physician to access the web page and access this information from a given patient to observe, analyze the data of the tremor and log out.
So here we're going to go into more of what we will be doing with the information that we're getting from the Pixie. So in the previous slides, we talked about how tremor is an unintentional oscillatory movement. When you think of oscillations, you think of something similar to a sinusoidal function. So with that approach, we're going to be taking the RMS amplitude of each axis of direction. So that would be for the X or Y place of the vertical and horizontal displacement. With these numbers, we'll apply it in the general systems performance theory, which we're going to get into in the next slide, which will basically help us get that one number that we need in order to help quantify our system. So we're going to start with the relationship between steadiness and tremor. We're going to use the inverse relationship law to compare the two. So one of your trimmer would be would be your steadiness, and the inverse of that. So with our system, using the General Systems Performance Theory composite, we're going to take those RMS amplitudes of the y and x direction, multiply them together, and by the inverse law rule, that will be our trimmer. So if we take the inverse of that, that will give us our overall steadiness for our system. So that's how those two numbers, that's how those two things will be related. And 1 over the trimmer will be your steadiness, and the same can be said for the other.
Okay. One of the problems that we initially faced when we were doing this project was the fact that we were using colored balls to track the motion of the hand. Well, that, because it is a vision-based system, not only was it picking up the colored ball, but it was also picking up everything that was on the other side of those tracked objects. So it ended up bringing a lot of noise into our system. And so the solution that we came up with was to take the normal contrast of the pixie count and drop it down to its lowest level to where it would simulate basically a black room. And in that setting, we use LEDs. So we use the LEDs so that it would be the brightest object in the darkest room. So that took care of all the background issues that we were having with it. And we were able to implement using red, green, and blue LEDs, which we found out, which we discovered, gave us the best data for this data. And so that's how we solved the problem of gathering all of the background noise that was inherent to the vision-based system.
As I mentioned before, the web page was constructed using Node-RED and all the calculations as well. So what is Node-RED? Node-RED is a visual tool for wiring hardware devices and APIs in online services in very interesting ways. Just dropping and dragging nodes, input nodes, output nodes, or function nodes into the workspace and connecting to each other with some JavaScript code in most cases. Node-RED was developed as an open source by IBM in late 2013. It's basically a flow-based programming model, as you can see in this screen. We use Node-RED to do some of the calculations. The way we did it is Arduino is taking the data from a pixie count in a raw data, and it's been transmitted to a local MQTT telemetry transport node that's in the local PC. That node, which is this, it's been received by the local PC as a raw data. This raw data comes through a start-stop button control from the web page. It goes through a series of function nodes where JavaScript is being used to parse the unwanted information. Once the unwanted information goes through the system, it's basically in the XY coordinates to proceed for tremor calculations, as we're going to explain in the next slide.
Okay, picking up where Sergio left off. So the X information and the Y information is going to be coming in these two separate nodes after being parsed out. And each one is going to go into a separate RMS calculation function. These functions are implemented using JavaScript language. And that's how we're doing our arithmetic and our math with the use of these self-created functions. So these, after the RMS values is calculated for each axis, it's going to go into a joining node, which sends out those two numbers in one array, and the final composite score calculation function just sends those numbers out until to the display for both the clinician and the patient to see if desired. Here's our current state. Our whole current state of our project as of November 21st. We've done a lot of updates, but this is what our system looks like as a whole. You have the Arduino and the motor, simulation of a severe tremor. So while the test was running, this was happening on the web page. This is what you can see on the web page. You can see the XY coordinates, oscillating back and forth because we're trying to simulate the tremor. And at the end of the test, after the end of the 15 seconds, you can see your results. So it was a pretty severe tremor, and of course your steadiness, the inverse will be very low. And this is what our dashboard web page looks like. Here are a couple of links to those places. There's our web page, our course website, and the video to be imported in. Thank you. I have
Because you're seeing the PC too.
okay, good.
Yeah, wherever you are.
Okay, I'm about to run through the test with a pretty severe tremor. Hit the reset start button.
I think that's it, isn't it?
See.
It stopped it, yeah, I thought.
Only 98. Okay, now I'm going to try to be as steady as I can.
Wow.
Oh. By a factor of 5 at least.